Welcome to clickmyproject.com. Let's discuss about the product. Our product is tunable CMOS delay gate with improved matching properties. This paper presents the analysis and design of a tunable CMOS delay gate with improved matching properties as compared with the commonly used current stator inverter, that is CSI. The main difference between these structures lies in the location of the current limitation transistor on the inverter's output rather than the side of the power rail. This improves the dynamic performance of the proposed output split inverter. That means OSI circuit reducing the influence of the MOS transistor mismatch on the generated delay time variability. A test chip including two arrays consisting of 512-16 stage delay lines employing the CSI and OSI gates has been designed for the fabricated in a standard 90 nm CMOS technology. The experimental results shows that the proposed OSI circuit is above 10 to 50% more accurate than the conventional current stator inverter, with no penalty in terms of the increased area, power consumption or complexity. Applications of the proposed circuits are the applies in the design of time to digital converters, that is TDCs, and delay locked loops readout circuits for the particular detection and time based asynchronous computation systems. Tunable CMOS delay gates and delay lines are important functional blocks and sub-blocks for the controlled delay time intervals, such as the delay locked loops. The design of a tunable CMOS delay gate, that is output split inverter OSI, lower impact mismatch on the delay time intervals than the commonly used current stator inverters, as we already discussed. The delay element were proposed to optimize the CMOS delay gate elements. New modified current balanced logic delay elements, that is MCBD, which are proposed without compromising the element complexity. Here, the optimization of the circuit performance in terms of parameter variability usually focus on reducing MOS devices mismatch by minimizing the variability of physical parameters of the transistor. A commonly used approach is transistor size scaling based on the assumption that the local variation averages which out when the gate area increases. It has been shown that the parameter variability observed between identically designed MOS transistors, which are relates to their gate size. Here there are two processes that depends on parameters, usually for the estimation of a short range parameter variably of closely laid out devices, that is called the fabrication mismatch, which are only the first area dependent component. So this is our process flow design. So according to this block diagram, our process is based on CMOS design methodology. So by using CMOS methodology, we are obtaining for the tool Tanner EDA. So in the Tanner EDA using TMOS technology, we are implementing the design as in the flow. So here initially after selecting the technology, that is CMOS technology, current balanced logic is designed and then followed by the black MCBD also designed. And regarding to the overall design, we have to analyze from the parameters, that means complexity analysis. From the complexity analysis only we can identify the delay. Let's discuss something about the tool. For this CMOS design based methodologies, we have to use CMOS design tool, that is called Tanner EDA tools. Commonly, Tanner EDA tools having lot of subdivisions, that is called SEdit, LEdit, WEdit and such more. There are lot of under devices. So in this we are using SEdit for circuit designing. So and then after we design that SEdit, while simulating the circuits designed will pass through the T-space that we can understand through the checklist generated through the SPICE code. And finally, while we are simulating, the timing diagrams will appear in WEdit. Hence, commonly for our CMOS based designs, we will use mostly these three edit things. That is, again I will say as SEdit, LEdit, WEdit and T-space. So we can design the circuit based CMOS transistors by using SEdit. Here, before we starting the simulation, we have to select a new cell. Here is the cell menu. Here we have to select the cell menu and we have to select new cell. So there you can select number of cells like cell 0, cell 1 up to cell n you can select. So each cell should contain different CMOS design. And next process is to set up simulation. Here this icon, while you are pressing that will leads you to setup simulation. In the setup simulation you have to set up maximum time duration for the design and nanoseconds based setup methodologies. After designing setup designs, we have to load the library files. So initially for the design of CMOS designs we need some CMOS components. Those CMOS components will occupy in CMOS libraries. That means CMOS libraries contains components of which required for CMOS design. So here you can see what are the components listed in CMOS library. While you are pressing add, it will leads you a window menu. There you can locate the library file where you have stored. So from the location where you have stored, you can select all components which you can need for your CMOS design. So after design of this cell, you can save the design, and while you are pressing run, it will leads to T-space. So through T-space you can see what are the checklist available in T-space. In T-space usually the components which you have used are listed in as a component code. That means you can see that as a program wise. That's why that T-space codes are called netlist. You can run either from SEdit or from T-edit. From wherever you are running, the output timing diagrams will show in WEdit. In WEdit you can see the waveforms which we have obtained for corresponding CMOS design. And also you can clarify what are the result parameters, and you can measure all the parameters which you need for the design from the WEdit. Thank you.